chat from time to time. I have my specific order of the review. I'll go to the old material first because I assume the new material is still fresh because the homework is due tonight and I solved some of the homework problems for you to make your life a little bit easier. I'm recording this meeting, so you will receive the notes. The notes are already posted actually in the modules for this review. I'm following the notes. And you will receive the video recording too. So the German saying says everything has an end except for sausage, which has two ends. That's the German sausage. So with this, I would like to welcome you to the final lecture of this course. And let's do the emphasis of the earlier material because you forgot it anyways. I also like the idea, I mean, this joke, I don't know if you find it funny or not, it's not my joke. But what I think is interesting is like in a computer game, there's always final boss. So final exam of any class, I feel like that's the final boss you have to defeat. And then you finish the computer game. Let's see. Let's remember old formulas. So we're just going to do lots of examples. Formulas are coming together with examples. Find different equations. That's what I hoped you have a list of formulas already created for yourself. You cannot use it during the exam, but again, visually, people remember locations of the formulas on the paper they have at home, and that helps them to remember the formulas during the exam. Find the equation of the plane through 3 points. We have A minus 1, 2, 1, B 0, minus 3 and 2, C 1, 1, minus 4. Equation of the plane solution. As you can see, this exam will have lots of formulas. So your brain should not freak out when you see equation of the plane. You should immediately imagine a piece of paper. I showed it in class. I hold a paper in class, maybe try to visualize that. And then I said, what defines a piece of paper? How do we know that's not any other piece of paper, a plane? 3 points define a piece of paper for sure. So what else? 1 point and a normal. So if we have just 1 point, then we have thousands of different planes passing through that point. But the moment you fix the normal vector sticking out from that piece of paper, then we have one specific piece of paper. And that's how we know that we need to create normal vector. And we have a point sticking from that, a point from which the normal vector sticks out. So to do that, we need to have vectors. Let's choose any random point that we're going to be using for the formula A. And the other, random here. I mean, you can actually put them on the axis if you want, but who cares? I don't really want. And the notation for yourself. Plane can be defined with a point. So you can choose any. And normal. Normal. And the normal vector, you remember, is getting from the cross product A and B. So we need to figure out those A and B. A and B, this A, this B. And then the formula, you're like, so what is the point to start this problem if you don't remember the formula? So we had lots of formulas. Some of them have 0 at the end. Some of them have D. Just try to remember one of them. To be honest, one comes from another one. So equals to 0 is the classic one. Try to go through from the idea y equals mx plus b. That was the equation of the line. A plane is a higher dimension. So m are derivatives, right? And then actually I would say 2 ways to see this. I would say like this. Mx plus b is a nice way to see it. But what helps me to memorize is x minus y sub 0.
Professor, I think you're muted.
Really?
I can hear you.
Oh, okay. Well, that was very scary. What I was just like talking for half an hour. Thank you for letting me know. But like, check. Maybe it's too quiet. Do you think it's too quiet?
For me, it's like perfect volume. I don't know about
Okay.
other people though.
So I don't need to yell in your ears. Okay, Sydney says she can't hear. Restart everything, probably just like a computer. Sometimes, what was the last time you used Zoom? If you need to update Zoom, that's when the problem starts. Mx minus x sub 0. Don't worry, for now, the material is very basic. So while you're restarting, you will see everything is familiar. I like to see it from this idea. Point, and then derivative. Derivative is multiplied by the shift. That's how I see it, at least, shift. You don't have to see it this way. So it's the same equation. Not the same equation, but idea is the same for the plane. We have normal vector n, and let's call it like not ABC, that's already reserved, M and T is reserved. Anything is good except AB. C, D, M. Oh yeah, okay, why not? Very random stuff. So I will call it C is multiplied by X minus X sub 0. And it's obviously a shift, so the point you choose. Plus D. Oh, you can do N1, N2, N3. That would be better. N1, N2, N3. That's component of the normal vector. N1, N2, Y minus Y0 plus N3, Z minus Z sub 0 equals to 0. So if you remember the formula, that's kind of the idea. So the difference is we use derivatives versus normal and so on. Like so. Okay, that's the introduction. And now you actually start working solutions. So step 1, I don't have those two vectors. I need to create AC and AB. You do tail minus the origin. So AC, which I call B, for example, it doesn't matter, will be 0. Okay, AC, 1 minus minus 1, 1 minus minus 1. That is, remember, that's a vector. 2, then minus 1, minus 5. I'm skipping this because I think you remember how to do that. AB is 0 minus minus 1. That's 1 minus 3 minus 2. That's minus 5. And then 2 minus 1 is 1. Nice. Like so. Now you create N. And you see like N is everywhere. Right now you're doing N for surface integral, the cross product. And we all start with this cross product. Cross product finds so many things. So I, J, K, and you put each 2 minus 1 minus 5 and 1 minus 5 in one order doesn't matter actually. The answer is correct. You perform the whole thing and you get the vector. Remember, it should not be a point. It's a cross product called a vector product. Now we have N point will be A, let's copy it again, minus 1, 2, and 1. Insert. Point goes to the shift and goes to the product. So we have 26, X minus shift, so plus 1, plus 7, Y minus shift, so that's 2, plus 9, Z minus 1. Equals to 0. And you know how to get to the D notation? If you need to the one with D, capital D. That is where you actually simplify everything. 26x plus 7y plus 9z. You distribute plus or equals that D. And D comes from, as you can guess, collecting those terms to get number. Kind of, that's it. That's a good short question. Sydney, did you get your volume? That's a good short question. Now, how about the tangent line? we had some equations, of course, not something from calculus 1, but we had some parametrization. Find the parametric equation. That was new. Parametric equation of the tangent line to the curve. And then we give you R of t is t squared plus 1, t cubed minus 1, t to the 4 plus t squared, and we give you a point 5, 7, 20. What are we asking here? No idea. Oh, that's the one we learned about directional derivative vector, points, so something like that. So what they're asking us to figure out solution. Again, I would say terminology is the hardest one. The brain need to remember what are they asking. Parametric equations, that's something involves t of the tangent line. So they want me to figure out this r, but for the tangent. That's what's happening. And we had two of them. It was the same, just differentiation. But either we had x of t equals y of t equals z of t equals like that. And all of them were mx plus b, you know, m1, b1, m2y plus b, and m3y plus b, something like this. So either this what we're asked for, or just that is going to be r, but since r already taken, you just don't call it r. You can call it r prime at the point, but it should be at the point, I guess. So at point, like so. So as you guess, the moment you see tangent line, you start with taking derivatives. That's at least you should remember that. That should be, I guess, the first step. So let's do that. That's the thing. If you start step one, if you stuck with what to do, start with something. It's either finding a point or taking derivative, finding parametric stuff. So in this case, I feel like it's very natural to start with derivative. R prime of t is 2t, differentiate each component, 3t squared, 4t cubed plus 2t. Got that. Now we need to plug a point. A point equals what? Well, in this case, I need to know t, but they gave me, wow, so tricky. They gave me not t. They gave me notation in terms of x, y, z. So unfortunately, that means I need to figure out that. So step 2 is an extra step. They could give me t, but they didn't on purpose. So they want you to figure it out. Find t. I would call it even t sub 0, because that's what we usually plugging. So the point, let's keep like this, point t sub 0. Do you know how to do that? Just solve a couple of equations. So if we know, let me think this way. This is nice, maybe like pink. T squared plus 1 equals to 5. T cubed minus 1 equals to 7. And of course, t to the 4 plus t squared equals to 20. Choose any two and solve them, and you will be happy. So it's going to be t squared plus 1 equals to 5. T cubed minus 1 equals to 7. Any two, you can do any. It's just usually the first two are simple one. I don't know. We usually put them in order. Who knows why? And then the third one is nice to check yourself. So, okay, t equals plus or minus square root 5 minus 1. That is 4. So plus or minus 2. I have two solutions. Well, I need one t. So others should give me like a strict choice. T equals cube root is not plus or minus. 7 plus 1 is 8. Oh, well, that's plus 2. We know that. So we only need plus 2. And we can check with the third one. If I plug 2 into the third one, 2 to the 4 plus 2 squared, it's better be 20 because it's supposed to be 20. And when I calculate, it is indeed 20. So 2 is good, check mark. T is indeed 2, put it in the box. Plug it in, give the answer. So we have step 3. Step 3 is going to be r prime at 2. That gives me 4, 12, 36. I'm plugging it into my r prime, which I should have put in the box. I always tell people put in the box whatever is important for you, so it's visually easy to find. Okay, why we were struggling with this? Because the last step is the answer. Step 4. To figure out the equation of a tangent line, we need point, and slopes. So x sub 0, y sub 0, z sub 0, and m slopes. But of course, everything in a higher dimension. So now you can write down x of t is, let me go back and see what's going on. And what t is plus, so we have, I was like, where did I look? Yes, this is where I should put in the box. I look here. Those are my slopes, which makes sense. Those are derivatives at the point, so slopes. The first slope is 4. The second slope is 12. The third slope is 36. Since it's slope, you always multiply it by x, y, or z, the variable. But in this case, everything is in terms of t. So it's t, t, t. That's how you kind of should remember it, because it's of t. And then there's a shift. The shift comes from the point 5, 7, 20. So plus 5 plus 7 plus 20, like so. And as always, you can always write it down in the vector form. 4t plus 5, 12t plus 7, 36t plus 20. Both are fine. So see the idea behind it, tangent. Tangent line. Tangent line is still the same as in calculus 1. Slopes are found from differentiating and plugging the point, and plus b, and that was the point given. Let's see comments. Okay, Sydney's back. That's important. Cannot go on without Sydney, okay? Next. Find the position of the particle with the given blah, blah, blah. Okay, I like this example a lot. To be honest, I like this example so much. Answer. Let's see. Example 3. I like this example so much that I put it in calculus 1 exam, calculus 2 exam, and calculus 3 exam. It just kind of increases the dimension, but I put it in every exam I give because students do really well on this question. So just like my students from my teaching are just doomed to have this example 3 times in the finals and 3 times at least in 1 midterm. So that's 6 times total. Find, no, 3 times, yeah, 6 times. Find the position S of t, position vector, okay, vector. Yeah, let me just put it here. Vector S of t, let's go to S of t, of a particle, if the device, for example, there's an asteroid passing by, record acceleration. So can you find how far the asteroid is away from the recording device, say a satellite? If we have given the acceleration, ACCEL, acceleration is also a vector, let's call it A of t equals 2, 3, 2. 232. And we know the speed, velocity. When it passed by, it's like there was a speedometer in space, again, on the satellite. And it recorded 40 minus 2 at the time 1 hour, for example, t equals 1. And that's not the end. And the initial position is 1, 2, 3. So weird, right? So why do we need even s of t if we know initial position? No, initial position was recorded at this moment when we saw the asteroid. So it's 1 hour, for example. We know how far it is. It is at the end of this vector 1, 2, 3, which we know how to draw, right? Which is like 1, 2, 3. So it's like over there. We know where the asteroid is. The asteroid is approaching us. We know the acceleration and speed. Can we figure out where is it right now while we're calculating all of this? And what is the function in general? The distance function of this article. So then I can calculate how far it is at every moment. T. Solution. That's called IVP, initial value problem. We'll teach it in calculus 1, and we have it again in calculus 2, and again in calculus 3. Initial value problem. That is a tricky way not to call it differential equations, but to be honest, it's just literally differential equations. Those are DEs. In some American schools, they just openly call it DEs. Which you take special class for that, but it's just like, this is the basic. So you actually now know it. You were introduced to DEs in your calculus classes. Okay, well, the idea is, you know that S of t gives you V of t if you differentiate, and gives you A of t if you differentiate twice. So guess what you need to do? You need to integrate and integrate back. S of t, sometimes called R of t. Step 1, we're integrating S of t to get V of t. V of t is integral. Let's see. We're starting with we're starting with acceleration, right? So V of t can be found by undoing differentiation of A of t with respect to t dt. So I need to look for the acceleration. Here it is, 2, 3, 2. So it's going to be 2t plus c. And since we're going to have many c's, you can call them c1, c2, c3, or a, b, c. 3t plus b, and then 2t plus c. So this came from A, integrating A. Now I need to find those c's. To find the c's, I need to figure out what to plug in, something that we know. Well, it says at t equals 1, at t equals 1, velocity v was or is 40 minus 2. So what kind of ABC will make it 40 minus 2 when I plug 1? So that's what you do. V at 1 becomes, well, at 1, 2, t is 2 plus A, 3 plus B, 2 plus C, but it's supposed to be given. It's supposed to be 4, 0, and minus 2. And that's what teaches you to use component by component equations. That's how computers calculate stuff. They usually just know that components equal to each other and they can solve for them. So 2 plus A equals 4. I can skip that solutions, but I will just write down 1. 2 plus A equals 4. So A is 2, B is minus 3, C is minus 4. You solve each, right? From here, you have like final version of the vector V. Vector V, do you know that everything has vector hats, right? V, A, S, V, A, everything has a hat. So don't be lazy, put hats. V is 2t plus A, but A is 2. 3t plus B, which is minus 3. 2t plus C, which is minus 4. Put it in the box, we need it. And you repeat the whole damn process. The only thing is they never told us what to plug for A. So that's the only thing to also think about. Let's do it. Step 2. Let's not use circles. 1 and 2. Step 2, we find S of t by integrating V of t dt. And that reminds you that at integrals, it becomes t squared plus 2t plus a. So those are new ABC. Nobody actually cares if you, again, call them again ABC. People do that. Well, I guess let's be creative. Everyone is so creative. BCD. It's not creative at all. I'm just using alphabet. Minus 3t plus ABD. Let's do something fun like M. Suddenly M showed up. And then t squared minus t plus j. Yeah, I like j. J is good. Good. So, but then you have that. And then you need to figure out what to plug. So it says initial position. Before it did not say the initial velocity. It says velocity at 1, but this time it says initial position. So if they don't mention what initial time was, we assume it is 0. That's a standard usually. I mean, it's nice when they clarify, but that's usually standard. So we plug S of 0. That's at least easier to calculate. That's going to be dmj, because everything just became 0 except the constants. Luckily, we don't have exponential functions here, so it's not. But that must be given. There's a vector given there, which is 1, 2, 3. Stop me if I'm too fast, or post in the comments. I will check that. The answer comes after this. Answer S of t equals t squared plus 2t plus a d, which is 1. 3t squared over 2 minus 3t plus m, which is 2. T squared minus 4t plus j, which is 3. And that is the answer. Beautiful. That's a position function. Not to be added. Not to be added. So about the letter J, I just learned today interesting things from video. So I and J share the dot. Isn't cool? So my name is Julia in English, but in Russian, I am Yulia. So you can write down. Of course, it should be capital. But is it funny that if you do with small ones, it shares the dot? How cool is that? Just realized. Be fun. Anyway, how about equation of a tangent plane to the surface? Example 4. That gives us something more new. Find equation of the tangent plane. Okay, now we increasing the dimension of the tangent stuff, the plane. We already had the plane, but my point is, and we increasing to what? The dimension of the object to the surface. X, Y, Z equals Z to the what? Oh, is it cube? Is that cube? Oh yeah, it is cube. At 1, 4, 2. Surface. And it's supposed to hit you. It's like a stupid fly. Really bad. We're supposed to remember what the heck to do. So that is the different equation. That was, again, still n. It's still normal. But we're going to do gradient this time. So solution. We need point for the equation of the plane. Again, you imagine a piece of paper. What do we need? A point and sticking out vector n. So we're going to need a point. The point is given, point, and n. There was an interesting idea of finding n as gradient to f at the point. So we're going to do it this way this time. The point is given as 1, 4, 2. Then also n will be found as a gradient of f at the point 1, 4, 2, because it's supposed to stick out from the same place. Gradient is perpendicular to the level surfaces. So we find partial derivatives, and then gradient will be sticking out because it's perpendicular to level surfaces. I'll show you during the process what it means. But at least now we remember what to do. Step 1. Let me just write down steps. Step 1. Step 1 is, I need this f, you know, so I want to have it f equals to 0 notation. So rewrite my surface. The surface is x, y, z minus z cubed equals to 0. Oh, that's the f. So f depends on x, y, z. Now, the point of this surface, level surfaces, level curves, that's what I'm trying to tell you. So the surface have level curves. Those are mappings. That's how the correct way to explain. Those are mappings. Then we want to figure out something that is perpendicular to that thing, something that sticks out. Well, gradient sticks out. That's the idea. I guess let's just write it down so you have nice notes. So my point is the gradient is perpendicular to the level surfaces or level curves. Let's go level curves, level surfaces. And what we're trying to find is so there's a point, right? Here's the point, 1, 4, 2. We're trying to find tangent plane, so a sheet of paper that touches the surface over here. Well, I want to have that normal, and we'll figure out that if you differentiate everything, that gives you gradient. Gradient gives you the perpendicular vector, so it's exactly, in this case, matches the n we need. That's going to be my n vector, of course. And f is also gradient vector. So step 1, we found f. Put it in the box. We need that. Step 2, let's find gradient f, del f. Partial derivatives, nicely written in the row. That's what we're talking about. Okay, let's just do that. And that takes you to nicely, your brain should be really good at this right now, to find partial derivative of this. Remember how hard it was at the beginning, and then you're just getting used to it really fast. I told you. Differentiate f with respect to x. That's going to be y, z minus 0. Differentiate f with respect to y, x, z minus 0. with respect to z, x, y minus 3z squared. See how fast you can do it. Now you plug the point. Step 3, you have n, which is this gradient at the point 1, 4, 2, which is, when you plug it in, 8, 2 minus 8. Just remember, take a pencil. It's very convenient, very helpful to actually not to mess up. Many of you are messing up what to plug in the exam, and I know that you know what to do, but you're looking at different stuff. So it's nice to take a pencil and actually write down what is x, y, and z and plug it carefully. Okay, put it in a box. After this, answer follows. Answer. The formula says, the formula is still the same as before. N multiplied by shift, n by shift, n by shift. So we have 0.142 and n 8, 2 minus 8. The answer comes exactly from the same formula. So it's going to be n multiplied by x minus x sub 0, that's 1, plus 2 multiplied by y minus 4 minus 8 multiplied by z minus 2 equals to 0. If the answer should be given with d, then you distribute everything. Oh, come on. That makes sense? Again, if I go too fast, let me know. Let me check the chat. Is this a free response question usually? Yeah, I cannot tell you that. This one has lots of steps, but it's an old material, so it can be both. It can be both. Chain rule. Chain rule. That's the one that I definitely can tell you that is there in multiple choice questions. Is chain rule, full of chain rule. Because that was important to learn partial derivatives. 4, 5. Let me put in a red. Chain rule. Listen, you can forget in a year or two how to create equation of tangent plane, how to create of the normal plane, but you remember chain rule, how to take partial derivatives, and how to create gradient. That is just really important. How to integrate twice, double integral, triple integral, that is very important. At least vague idea of flux should stay with you in a couple of years, especially if you're engineer and physics major. Which again, I was talking with a senior professor, very, very successful professor in Ukraine, who was supposed to become our Minister of Education. She's a mathematician with PhD and everything, of course, like full tenure. And she doesn't remember flux really well because pure mathematicians don't work with flux that much. Applied do, because it's physics and of course engineering. That's where flux comes in. So I showed her and she's like, oh, that thing. Yeah, I remember that thing. We just don't really use it in pure math that much. So now you know. Chain rule. Basically, I threw at you any function x, y, z, and let's do one more variable, w. And then I just made it up, you know, x squared plus y squared plus w plus z plus 43. Numbers, literally. Why not? Find, and now imagine I can ask anything. That's the thing, like, oh, that's not yet. Where? That would be easy. If I just ask you to find derivative with respect to x, y, w, or z, that's easy peasy. We just did it in previous examples. But each of them has some kind of math going on. X is a quadratic function. X is quadratic function s squared. Y is a quadratic function r squared times s squared r. What is this r? Oh yeah, r is a second variable. Z is r cubed, w is r, an exponential function of s. That is a crazy idea. So I see 4 letters right away, and then 2 letters more after that. That gives me 4 plus 2, 6 dimensions. as input. Think about it. But they are dependent on each other. So the output is F. Output depends on 4 variables, X, Y, Z, W, but each of them only depend on 2 variables, S, T, S, T, S, T, S, T. But imagine each of them also can depend on 10 variables. And some of those 10 variables can depend on something. And everything depends on time. That's not. Everything depends on time. Think about that. So I can continue as much as I want. It's just going to take too much time. Solution. What to find? I can just ask for anything random. For example, df, ds. If I ask find s or t, that means they ask me to dig into this lowest level. So I don't recommend you to build this tree. I don't know, many professors teach it, and I ask so many people. It confuses more than helps. I'm kind of pretty sure about that. But if you know, if it helps you, then go ahead and do it. But I don't use it. I just look at this first equation, stare at it, and just start doing my job. So df, ds. The first idea I see, I first need to look which variable actually depends on s. I need to go to those pockets. Well, not all of them actually do. X, Z, and W. Oh, X, Y, and W. You can write down all of them. And actually, fine, let's not skip. It's going to be too complicated to explain. You could actually assume that Z does not depend on S. But I guess you can assume it does. It just multiply. It's like S times 0, something like that. Anyway, partial derivative with respect to X, S there will be 0. S. So I just start differentiating everything I see. Chain rule tells me x squared gives me 2x, but then times the derivative of x with respect to whatever they ask me to find. I keep looking back to s, and I see that. And then I need to look to the variable I need. Since I'm talking about x, I'm looking at x. That is s squared. Derivative of s squared with respect to s is 2s. Boom, done. So if you want to see it through the tree, I did this. I went to X, and then they went to S. Now I'm going to go to Y, and I'm going to go to S and to Z, and I'm going to, I don't know, I feel like it's easy just to do it right away. Somehow I'm truly convinced on that. Also, many of you write down formulas. You can do that if you want, but I think doing it right away is easier. If you want to write down the formula, we took partial derivative of f with respect to x times partial derivative of x with respect to s. Remember, times means and. That's why chain rule is and. While plus means or, that means we can have other pockets where s is hidden. So, or, let's look at another pocket. Another pocket is y function. So 2y comes from y squared times partial derivative of y with respect to whatever they're asking me. And they're asking me about s. So I see r squared as a constant. It's going to be r squared times 2s, which is basically 2s, 2r squared s. More plus the green color plus derivative of w with respect, just derivative of w basically. That's 1. And then w with respect to s. What am I doing? W with respect to s. I'm looking here at the last equation. R e to the s with respect to s can be r e to the s. So go e to the s. Nice. And the last one, z. Derivative of z with respect to z is 1. And then you look at z and differentiate with respect to s, that's 0. So I would just completely who cares. And that's not all. 43, derivative of 43 with whatever you want is 0. So that is the answer. You should have 3 terms. Here they are. 3 terms. Can you do that? because that's already there for sure. Like chain rule was important. We don't expect you to memorize formulas, but we expect to memorize the process. Or you know also why it's so important. Like you would say it's so technical and so boring. Why we think it's important to teach that? I would say because you will see lots of articles in any STEM major full of chain rule. And it's going to be multivariable chain rule with respect to temperature, viscosity, flux. You will have torque. You will have electromagnetic fields, and everything will have partial derivatives there. You saw the presentations on Tuesday. Traffic equations have partial derivatives, chain rule, machine learning, Fourier transform, anything. So image processing, noise canceling. So at least we want you to figure out and recognize what is happening. That is the goal of learning partial derivative in this class. So at some point, we want you to read the scientific article and understand like 70% of it or more. That's the goal in the first octant. I like to put first octant on my exams because people are really good. Everyone are really good with first octant, so I feel safe to put it in so you don't fail. Only several people forgot what first octant means. The first octant means if you, well, first of all, like what the heck we're talking about? Oh, we're talking about the ball. The ball is not a sphere. The ball is whatever is inside of the sphere. So it's a filled in solid sphere, right? But that gives you a hint that we're using spherical coordinates. I mean, come on, x squared plus y squared plus z squared. Of course, it's going to be spherical coordinates. This just makes sense. So they want you to calculate this integral. That looks like from exam 3, and that's a problem, right? Where E is the ball radius 2 in the first octant. Okay, if we know it's spherical, let me first do this note. What does first octant means? That means X is positive or 0, Y is positive, 0, Z is positive, right? So that also gives you the idea. So it's the first cube of the 8 cubes of 3D Cartesian system. But then if you talk about rho, theta, and phi, rho is originally always positive. So that stays the same. That makes sense. So we can go as far as you want, but in this case, until 2. Theta is usually from 0 to 2 pi. But now you need to remember what it means to have first octant. So let me sketch it. First octant looks like that. X, Y, Z. In 2D, theta goes from positive encircling like this. That's my theta angle. It cannot go more than pi over 2. So I'm crossing this, and it's going to be pi over 2. That's, oh yeah, that's what was in the exam. I remember that, exam 3. So, and then phi. Phi is usually between 0 and pi. Right? That's, you just need to memorize that, from north to south pole. So phi is going down. That's like that. Phi is actually going not up and down. It's going down. Phi. So I'm going to cross that. And then also have to restrict it to halfway through, which is 5 and 2, like so. Make sense? 0. And the second thing you need to remember is our equations. So in this case, you actually don't, but they are, in general, in the exam, I asked you, what are the equations? And I will ask you if that can be a problem for the written response to show me what X, Y, Z become. So let me move this a little bit. For the spherical, those are classical known equations. Solution. Spherical coordinates are X equals Y equals Z equals. I remember it this way. R cosine theta, R sine theta. But in this case, we're moving to rho because R was in 2D. How far I am from the node in 2D, while rho is 3D. Rho. So rho cosine theta, rho sine theta. I remember that. Then the third dimension, or spherical, so this whole sphere thing, adds sine phi, sine or cosine? Do you remember? Which one? And cosine phi. Why this? Okay, oh, there was a question. I missed the question. And will we have to plug X and go back? Oh, yeah, this, I totally forgot to check questions. Duh. Yeah, you have to go back to the original variable. I forgot that step and I forgot to check the questions. Okay, that's a good point. Let's do that. Well, I can do this. I like cheating. Yes, on the second exam, I gave you the answer and I said, answer only in terms of X, Y, Z, right? So that means you cannot give me, no, the answer in terms of S and T, the very last variable, S and T. Because if people would ask me, okay, I just want to plug S, temperature 17, and R, it's not T, and R, with their viscosity is 8.3, I don't want to go and look for each equation where what is X, what is Y. So just give me the answer in terms of those two variables. Then yes, it's a good point. You have to plug everything in. So it's going to be 2 times 2 is actually interesting. Did I have it in my note? It was in my notes. I just totally ditched it this year. So someone should have unmuted themselves and just tell me. It will be, let me not simplify it so it was more obvious. 2x, x is s squared, and there's also a comment about fourth term, times 2s plus 2y. Y was r squared s squared multiplied by 2s. All of this can be simplified, plus 1 r e to the s, like so. Let's see. So there's something is missing. So that's what people are saying. Something is missing. Let me check. X is correct. Y, derivative of y is 2y times y with respect to s. Correct. Derivative of z, 1 times r, oh, w. W goes first. Okay, good. Derivative of w is 1 times r e to the s. And derivative of z is 1 with respect to s. R cubed is 0. Yes. So what is the question? Let me put this in the box and ask. And check the chat. Is this correct? Why, we should not have 4 terms, as I understand, because this guy, z, does not depend on s. So technically speaking, it's there, but it's 0. So I just kicked it out. So we have 3 terms. We have x, y, s, t. X, y. We're supposed to have the ends x, y. Trying to figure out what are you asking about. I only was asked to find derivative of partial derivative with respect to s. So I'm going to differentiate everything with respect to X, everything with respect to Y, everything with respect to Z, and everything with respect to W. Since there is no product rule or quotient rule, it was kind of easy. They were also in order. And then each of them only with respect to S, only with respect to S, only with respect to S, and only with respect to S. Yeah. If it's df, ds, df, ds. Yeah, so we're looking for df, ds. I'm not really sure what the question is. Maybe you should unmute yourself and ask. X, Y, S, SR. Yes, we have from here terms. That's what I see the problem is. Yeah, it's an English problem. Terms and variables. I meant to say that we have 3 terms, 1 term, 2 term, and 3 term. But yes, you're right. There are 4 variables: X, Y, Z, S, T. So the final answer is, when you simplify, you should have only 2 variables, S and R. So what is the final answer? That's what I'm asking someone also to check the final answer. 2R squared. I think I lost something, right? I also feel that way. So let me see. 2x is here, 2s is here, 2y is here, 2s is here, 1 is here, r e to the s is here. R squared, 4s cubed, 4s cubed plus
I think you forgot the r squared, like, so it says 2y times r squared 2s. And
that one. Wait. 2y, that's one, this one. Yes, see, something was missing. Thank you. Very good, very good. It was here right before. Let me put it here. R square was missing. I felt like it was not long enough. Okay, that looks like 25. 2s. Yeah, definitely keep an eye on everything. Someone simplified for me. 4r to the 4s cubed plus r e to the s. Very good. Yeah, very good. Just totally ditched some term for no reason. I'm not an evening teacher, so I always tell it to students. That's why I never request classes after 2 p.m. because I tend to make like weird small mistakes in the evening. So keep an eye on that. Good. Going back to spherical. So is it sine or is it cosine? I actually wanted you to tell me, is it sine at the end or is it a cosine at the end? So I want you to question that. I want you to question yourself and me. Which formula is correct, sine or cosine? Is it cosine? So I'm talking about here, over here. X equals rho cosine theta, sine phi or cosine phi. I want you to kind of question that, because on a test you will. On a test you will zone out, get scared. So like try to figure out some kind of way to remember. It should be sine. What I remember, they should not be the same right away. They're the same for y, but they're not the same for x. So remember that x is the most diverse one, which means everything is not matching. Rho cosine theta sine phi. Then y sine theta sine phi. And then since we never wrote cosine phi before, that's at least how I memorized it. Cosine phi goes at the end. So everyone have their own way to remember. I did it this way. Now what we do, lots of steps. I mean, not that many, but step 1, know the formulas. Step 2, rewrite your function f. F is whatever is inside of the integral, right? So f. Sometimes they call it capital F, dx, dy, dz, like that. So rewrite it in terms of whatever you just wrote. Luckily, You don't have to recalculate everything from scratch because there's a known property, x squared plus y squared plus z squared gives you rho squared. Yay. That is why it's not a coincidence. We give you such a nice function f. So on the test, you don't spend too much time on it. Rho squared squared. So it's to the 4. Nice. That's like a very good thing to have. And you can start building the integral. Step 3, build the integral. Multiple choice usually tells you just to choose integral from the list, but you still need to know how to integrate in case it's not. In case it is integrated. Integral, integral, integral. Rho to the 4, d rho d theta d phi. Tell me the mistakes I made. So like we definitely know what is happening. Can you tell me? You see that you should not trust people. So first of all, no tail, right? I call the tail. I like this idea because it is the tail. It's called dA in many cases. dA for spherical, it's part of the formula is, what is the tail? Rho squared, people are writing down, sine phi. That is something unfortunately you have to memorize. The tail is rho squared sine phi. Something else is not normal, I would say, not usual. D rho, d phi goes first, or d theta goes first. What do you think? And it doesn't even matter. I remember that the theta always goes last because that's the original thing we learned from calculus 2. So it goes to the very end. It matters if we have functions, not just numbers as limits of integrations. So that is part of the formula. If you Google spherical coordinates, they will give you 3 formulas. This system, x, y, z, the r square formula, and dA. And you know what it means. That is a tail for the triple integral. So let's switch the order. D phi, d theta. And the tail goes inside rho squared sine phi.
Question.
Yes.
Wait, for theta and phi, won't they always be like the bounds though? So like, won't they always have numbers?
Yeah, not always. We just give you nice examples when they are numbers all the time. I think we never had example for you guys when they were functions, but they sometimes can be. That's why if phi is a function, you cannot put it at the end. But yeah, I mean, good point. If all of the numbers, then it doesn't matter.
Okay, thank you.
So when, yeah, good question. So on the test, when someone messed up the order, I did not take points off because in those examples, it is correct. Since they're all numbers, I'm not gonna take points because it's correct. But if someone has a function minus square root of rho squared, whatever, then you cannot put it at the end anymore. Why is rho to the 4th power? Shouldn't be squared. Thank you for asking. So originally it was rho squared, but then when I look here, it's again squared. So it's squared to the squared. Let me put it there. I was wondering if anyone actually noticed what is this. Thank you for asking. Yeah. Okay, and then you just figure out the borders. Rho is the simple one that will give you radius, unless you have to find, of course, like intersection or something. That's from 0 to 2. Remember, it's positive, so don't do something weird, like from -2 to 2. And then everything, so originally phi should be from 0 to pi, and now you have to figure out the corners. In this case, we said first quadrant, so it's from 0 to pi over 2. And theta is from 0, should be 2 pi, but again, the first quadrant, should I put it like first quadrant. See, they always put this number 1, not wrong. Or what's anyway, you got what I want. I forgot English too. Pi over 2. So now you integrate quickly. So let me check my notes so I can speed up a little bit. This one is easy. Since all of these are numbers, you can break them into 3 integrals, and each can be used. You can use a calculator to calculate it, but if not, it's not very hard to calculate. Don't forget your calculator and final exam, like all of your exams, physics and everything. Like that's just going to be very upsetting if you forget calculator. I will do theta first. Theta, I don't see any theta inside, so that's going to be 1 d theta. Then I will do phi first, basically in order. Phi has sine phi d phi. That's it. Then I will do rho from 0 to 2. Rho has rho to the 4 times rho squared is rho to the 6 d rho. Yeah, rho to the 6 gives you rho to the 7, plug 2, you get the number. The first guy is 2 pi, the second guy is minus cosine, plug pi over 2, blah, blah, blah. You get 64 over 7 pi. Nice, brilliant. I'm very proud we finished this problem. So can you do that? I think that was exam 3 response. Okay, we have to give you, I mean, to be honest, I can tell all of those problems are on the test because there's lots of questions on the test. There's like 15 multiple choice and 3 free response. So 15 plus 3 and free response sometimes have A, B, C. That is 18/20 questions. So imagine if I take one problem from topic, it's going to be everything is there. So yeah. Which means finding minimum maximum is always also there. 7, maximum, minimum, and saddle point. That topic is very successful. Everyone liked it, right? Saddle point. So I feel very, I feel good putting it on the test. Because people usually good at this. I give you a function, you know what to do. F equals x cubed minus 3xy plus y cubed. Find everything. Find whatever it has, you know, it might have nothing, it may have just been, or have everything. Solution. Just like when calculus 1, you start with finding critical points. Critical points are coming from derivatives. It's just now they are partial derivatives. So what? You just find partial derivatives. With respect to x, it is 3x squared minus 3y. With respect to y, it is minus 3x plus 3y squared. Now the problem is you need to solve them. Critical points are coming from taking derivative and finding where they are 0 and d and e. When you never gave you example when they're d and e, but in calculus 1 with d, there was a fraction and you had like x minus 1, something like that. Then you also have to check denominator. But this one is easier to solve. So you see this as a equation with system of equations with 2 unknown, and you solve them. Any method you know. The simple, the substitution method, elimination method, everything you learn in pre-calculus class. For example, I would just divide everything by 3, just like annoying to have 3 everywhere. X squared minus y equals to 0. X squared minus x plus y squared equals to 0. And then you can have different methods. In this case, I would solve for y and plug it into y in the second equation. Y equals x squared. Then we will have minus x plus x squared equals to 0. That is x to the 4 minus x equals to 0. Remember, you don't divide by x. You factor it out. If you divide, you will lose that one solution, which is 0. Factor out x cubed minus 1 equals to 0. You have 2 solutions, x equals to 0, x cubed minus 1 equals to 0. X equals to 0. No, this one I will not put in the box. And x cubed equals to 1. That is not plus minus 1. So we have unique x equals 0 and unique x equals 1. You're supposed to check if they're in the domain. Critical points have to be in the domain, but there was no restriction on this function, unless like it was like something, oh, don't go beyond x, x should not be positive. Then you had to exclude y0, 1, for example. So we never gave you that either, but actually from calculus 1, you maybe remember that. Now you need to find the next pair. What is y? What is y? So you plug in each equation. In each equation, 0 gives 0. So that's the easy one. When x is 0, y equals to 0. And what happens when x is 1? Choose any to solve. When x is 1, I have 1 squared minus y equals to 0. Guess what? Y equals to 1. Convenient. So we have two pairs. Critical points. Two pairs. 0 and 0. And 1 and 1. That's what we had in exam 2 free response questions. Woods review will be posted later online. Yeah, sure. I'm recording everything. We'll post in modules. Let me actually check. Is this recording? Better be recording. Yes, it says recording. Good job for checking. That is step 1, critical points. Did I put step 1? Step 1, find critical points. That already took forever. Now step 2, classify them. Classify critical points. That also takes time. So everything is just slow when you increase dimensions. That's where the matrices comes in. We only gave you 2 by 2 matrices, but if you increase dimensions even higher, you will have 5 by 5. That's where the Jacobian comes in, working with matrices, eigenvalues. It's really cool, actually. That's linear algebra goes that, and discrete math goes there. So we're gonna use second derivative test. Second derivative test. Why? Because why not? Because D consists from second derivative xx, xy, yx, yy. That's why. So we need a second derivative. And now remember, we're going to check the sign of that. If D is negative, that's a good news, right? If saddle, because then it's a saddle point right away. Saddle point. If it is, let me change the color. If it is positive, then you have to check one more step. You're checking this guy, fxx, and then you have 2 options. It's also positive. Then you have one positive, another is positive. That's a smiley face. That is minimum. And then if that guy is negative, then you have one happy eye, another eye is closed because someone hits that person in the eye and gave them black eye. That is a maximum, like so. Again, sense of humor helps people to memorize information. That's literally research in psychology department. And by coincidence, our class was in the psychology department build. So that's why I know, because I have a PhD friend there. Here it is, here it is. But also the thing is, we need to check at any point, every point, at every critical point. So that's what classification is about. It's called a test because it just tests all those points. Stupid to fly, it just really pisses me off. Where did it come from? Anyway, we're gonna find second derivatives first. So I'm gonna go to the first derivatives. Oh, here they are. There, see, I put them in the box. How smart is that? And I'm gonna find fxx. Fxx, you can even find them here if you want right away, because why not? Xx. Fxx is 6x. Fyy is 6y. And then fxy is -3, and you can check that fyx is also -3, but you don't have to find the second one. For smooth, nice, continuous functions, those second partial, they call it partial mixed derivatives, are the same. Okay, so we have that. Xx is 6x, y is 6y. xy is -3. Put this in the box, we need that. Many of you have different strategies how to proceed after that. I do it this way. I built D without any numbers first. Some of you putting numbers right away, which is 1, 1, and 0, 0. I put the general D and then I start classifying. I think this way it's easier. 6x, 6y, -3, -3, repeated twice. Cross product 36xy -3 times -3 is +9. That is my D in general. And now we're gonna check step 3. Now we're gonna check the sign for each point. And we have 2 points, 0, 0, 1, and 1. So D at 0, 0 is -9, negative, saddle point. So at 0, 0, we have a saddle point. D at 1, 1 gives you, I don't care about the number, I care about the sign. So it is 36 minus 9, which is positive. That is either min or max. So no idea. Need to add one more information. Fxx at this point, 1, 1, is going back. Xx is 6x. 6 times 1 is 6. The most important, it is positive. So that is a minimum point. Minimum point. Just minimum. Enter. I ask you on the exam to enter x, y, z. And that was confusing for people. So let's figure this out. X, Y, Z. 0 is x is 0, y is 0. Where z is coming from? Z is the output. It's the third dimension. This is z. So I'm taking the critical point and plugging into the original function. That gives me 0 in this case. Let me put it in red, 0. And this comes from original. This is the saddle point. Saddle. Then x, y, z. 1, 1. I'm going back, plugging 1, 1. 1 minus 1 plus 1 gives you -1. Really? 1 minus 3 plus 1 gives you -1. -1. That is minimum. Can you do that? That is, can you do it on Tuesday, please? No questions? Okay, that's optimistic. Now, more. Let's go to the news. Let's go to the conservative, not conservative, FDR stuff, blah, blah, blah. That stuff, that kind of stuff. PQR, curl, divergence, potential functions, all of that kind of stuff. That was hard. That was like lots of information just recently, right? And then fundamental theorem for line integrals. Anyway, so line integrals basically. Integral over the line. Line, so we have surface integrals we just learned recently. And the previous version was line integrals. We integrated before over the line. If there's a line, and you want to find area below this line, that will be this fence and it's curved. So it's a beautiful idea if you think about it. Now, that had notation integral over C. This red part is C. F dr. And then we had several ways of doing it. Green theorem, potential function, and fundamental theorem of calculus, or use the formula. So let's kind of talk about that. I have like notes here. Easy to do direct. So first, we know the formula. F, figure out the parametrization. That's the one you don't like doing that, right? You figure out R, plug it in, times R prime dr. So for you to know, I definitely need to mention that. The idea is we keep reusing derivatives, slopes, basically, or tangent lines for many things. That's where the R prime comes in, right? So just recently, the new formula we have, a double integral, and we had capital F. That was a, don't write it down, though. Don't write it down. The surface integral literally has exactly the same thing, but it had two of them because we increased the dimension, du dv, right? So because it's a surface, not a line, it have more dimensions. We still do exactly the same thing. We find parameterization, plug it into the function, but then we find several derivatives because we have several variables. We cannot just do R prime, so we find several of them. And then I would say the flux doesn't even have the surface integral with capital F, doesn't even have marginal of the cross product. If capital F is here, we're going to talk about it a little bit soon. So, and then with a small f, then yes, we have marginal, blah, blah, blah. The idea, my point is this tail having exactly the same idea all over again. We're using tangents because when you zoom in to the surface, tangent is really close to what we're talking about. So why not to use tangents to approximate stuff? Yeah, that's my point. So that's why it might help you to memorize that the formula is the same. It uses R prime dr all over again. But if you have more variables, then you find partial derivatives and find cross product. Okay, so this is the formula. Here it is. Look at that. It looks beautiful. But then, do we always use it? No. So let's figure out when we do not use it. That's called directly. Question: is it easy to do it directly using this formula directly via means using star, and let's call this formula star question mark. If the answer is yes, then guess what? You use the formula f r prime dr. That is a dot product, by the way. F r prime dr. But what if it's not? No. Then you're like, okay, what if we don't even have R? Then what do we do? That's different ideas. So if, second question, is F conservative? Is conservative. Conservative. Well, first of all, you need to know how to like check that. But it is easy to check using partial derivative with respect to y, partial derivative with respect to x. So mixed partial derivatives, just like before, should be the same for nice functions. So I put them here. These guys. Same, so green theorem, actually, it comes from there. That's literally the whole idea. We do that. If the answer is yes, right? Yes. Then we can do fundamental theorem of calculus for line integrals. Line integrals, that's the long name of it. Fundamental theorem of calculus for line integrals, which is you find small f integral f dr equals small f ending point minus small f starting point, where you need to find first f, which is potential function. Potential function. If it is not conservative, then maybe it's possible to use Green's theorem in 2D. That was that thing, remember? Do you remember the Green theorem? Let me write down a nice looking formula, or you type it somewhere. Let me see. P minus PQ minus QX, so Green's theorem. The Green's theorem says integral P dx plus Q dy equals, and you go to double integral instead, and double integral, you take second term. So F, I would, yeah, they should kind of make a point here. I was like, what is P and Q? F consists from P and Q in order. That is important to know. That's where it's coming from. P is P is your first input, so it's X. Q is the second input, so in terms of Y, but then you mix them up, taking with respect to X, and this one will be with respect to Y. You find a difference, which is dP, and then you integrate, you have double integral instead of first integral dx dy, instead of, yeah, and then you can use polar, blah, blah, blah. That works, you need to figure out the orientation, also it's positive orientation, is counterclockwise. If it's negative orientation, switch the sign like that. So maybe like, let's put this. That's positive. I always remember that for some reason, against the clock is positive, like who decided it was a good idea. What do you think about that? That's not solving anything. We're just kind of like reviewing stuff.
I have a question.
Yeah, I remember just
when you say like to switch the sign, like switch the sign of what?
Yeah, that's what I just realized. So let me move that. That's important. What I did not show is this is over C, the same C I was mentioning here. Let's line integral, right? So interesting that we're going from one dimension to dimension. Well, not really. C is a curve, but instead we're going to D, which is domain. So I should mention that C. Let me change colors, or else everything looks the same. C is this. C is this thing in green, while everything in yellow inside is D. So that's where the idea is D. So now answering the question is, what do we switch? That comes from the parametrization, if you remember, or there are two different ways of doing it. I think everything. As I remember, you just switch the sign of the result. Now, since you asked, now I'm kind of hesitating, questioning myself. Also interesting that in here, we don't call it P and Q. I always wanted to mention, but it's just never been a chance. It's actually called M and L. I don't know why people did not agree on that. And also, I never mentioned that line integral on the closed curve actually has notation with a circle in it. So if you saw, I never mentioned, I don't know, they did not mention the books. I decided not to traumatize people with a new notation. But it's a known thing that if line integral on the closed curve has this circle inside of the integral sign. So when you see my last announcement, I attached the old notation we just learned, and we actually learned that notation. It's there. Let's do example and okay, F. So we have C. If C, say, is positive, we keep it as it is. But if C is negative, yeah, I'm pretty sure we're just switching the order of these guys, basically, or just switching the sign to make it positive. That's a very smart question. Okay. If I'm understanding the question, when it's oriented in a negative direction, you have to make the answer negative. You just change the sign, basically. Yeah. And if you get a number inside of the integral, after subtracting, you can just multiply that number by area of the closed integral. Yes, exactly. That is smart comment made there. That sometimes you don't even have to figure out. That's stupid. We don't have to figure out So let me put a huge kind of thing. The whole double integral. You can do it faster. You got a number multiplied by the area. So inside of the integral, you can just multiply it by the area of the closed path. Exactly. So we had it in the examples in homework that we had some kind of number, let's call it K, and you can just multiply it by the area. Okay. And constant times the area. Sometimes, so that's if you know it's a circle, you know it's pi r squared and so on. Okay, good. Let's keep going. Where is my notes? I lost everything. I definitely want to go at some point to the recent material to maybe clarify something, but I put effort and actually solved some of your homework, which was hard. That homework took longer than I thought. So hopefully you check those out. What are we doing here? We're choosing what to do basically for the specific example. Let me give you a specific example. That is example number 8. Example number 8. For sure, we're gonna give you line integrals. That's kind of really important topic. Probably several. Find CFDR, where F is Y, Z, E, X, Z, E, X, Z, X, Y, E, X, Z. Oh my goodness, that's a lot of stuff. And then if you're lucky, R is given. R is t squared plus 1, t squared minus 1, t squared minus 2t. And they even gave you the t from 0 to 2. That is such a big luck. So if it feels like, oh, I have more notes to tell you about that table. Feels like because of that, we can just, we can find potential function, use fundamental theorem of calculus, or you can actually do the R prime, like all of this is fine. I guess if I ask you in the free response to find potential function, you don't really have a choice. You actually have to find. So before we start, I just realized I have more things to say. We learned curl after that. So check out. From the conservative question, so let me highlight it, conservative from this question. We actually have several topics. In 2D, we have a formula, let me put it in the red. P with respect to Y equals Q with respect to X. I already wrote it down, right? Conservative. In 3D, we have a curl that checks if it gives you 0, 0, 0. Why? Because in the curl, the terms are all differences, Py minus Qx and so on. And curl has a formula. So if I ask to find curl, which I am asking right now, we're gonna practice curl right away. Divergence and curl. Or they just even check it. So this is a 3-dimensional object. Did you notice that? This is not 2D. I have PQR. So A, find this. Find the integral solution. Let's check if it's conservative. Question mark. To check if it's conservative, we in 3 dimensions, we want to find curl. Because like even if you try to do the 2-dimensional, it's not enough. You're only gonna check this. Curl uses PQR. So our F consists of PQR, like so. 3 terms. Curl of F is I, J, K, partial X, partial Y, partial Z. And then you actually write down Y, Z, e to the X, Z, too much writing. Let me write down PQR. You got it. You just copy it there, PQR. And you do the thing. You actually carefully differentiate everything and collect stuff. And it's better be 0, 0, 0 to get conservative. If it is conservative, Now we can find potential function, for example, especially if I ask you to do that. So we have lots of videos on potential function. Maybe just do it by yourself. Remember, I have lots of videos. You integrate each, you don't differentiate. Many people, unfortunately, differentiated it, but potential function was already differentiated. So we have capital F. We want to find a small f that was differentiated. So to find a small f, you need to integrate the given stuff. F will be integral with respect to x. F will be integral with respect to y. And f will be integral with respect to z. And not just the whole thing, but the specific component, right? Because this is P, this is Q, this is R. So P, Q, R, like so. And then you collect the terms without repetition. My way is faster than the way they do in the book. And then if you have potential function, which is in the case actually pretty easy to find, I see in my notes. You plug the point and they gave you the point. They gave you 0 and 2. You need to find, though, the 3-dimensional point notation. Plug it into the original function. Plug the end minus beginning, and you're good to go. Yeah. What do you think about that? So either negative. Let's do example where we have to parameterize things. Yeah, exactly. I can agree on that. Let's do that. Oh yeah, this next example, number 9. Actually.
I have a question again, sorry.
No, good, definitely.
Yeah, with like the line integral stuff, you know how it was like something about when it's like a closed path, it's 0, but like when does that specifically apply? Because like we said down below, like if it's a closed circle or whatever, we can calculate the area. So then that line integral is not 0, but when is it 0? With like the closed path thing.
Yeah, the closed path thing. That was the topic about that you can use any path, it's independent of the path, blah, blah, blah. Okay, let me mention the correct terminology, that would be better. Line integral closed path. So if C is a closed path, basically it's a loop, and we're traveling over C, and it brings you back to the starting point. So that's important that we have to complete the cycle, or else it's not going to work. Like if we stop halfway through. We can integrate around starting at any point, and since the starting and ending point are the same, the line integral gives you 0. So it is 0 if we complete the cycle. That's called fundamental theorem of line integrals, blah, blah, blah. No, fundamental theorem of line integrals is anything. You can plug the end in the beginning, but we not always complete the cycle. For example, when they gave us, let's wait for 1 minute. They gave us t from 0 to 2 minutes, from 0 to 2. So they told us while my timer is running for 2 minutes, we're going to be walking through this path. Say it's like a hiking path. We're not necessarily going to complete it. Then it's not going to give you 0, even though it's closed. But if it is closed and you're traveling, and it doesn't matter even where you start, because the starting point and the ending point is the same, by the definition, by the fundamental theorem of calculus, it will be f of the ending point and f at the starting point, which are the same. That gives you 0. That's where it's coming from. So if you ever complete the trail and you end up to be at the beginning, by the same formula, end minus start, and is a start, so it gives you 0. We do not give you lots of examples like this. It's just kind of fun to know. It goes into other classes mostly. Most of the time, why would you? With the, I think, electromagnetic stuff and what's the particles, they do tend to go back. But again, even in physical applications, why would you need a complete beautiful cycle? Usually It's cycling and then it stops somewhere. That's why we don't always have 0. Yeah, does this answer your question?
Thank you.
First question, yeah. Where do we plug t? But we here have t. Oh, that's a good question too. So if completed the, what is it, loop? Yeah, if you complete the loop, it gives you 0. Nice. And of course, it's independent of the path. You go there or back, it gives you 0 or -0, which is still 0. Because ending point is starting point. So that's why it's also independent of the path. There was the question is, when you want to plug the end and the beginning, you usually plug the point, but we have time, t. It's not necessarily time, but it's easy to see it as time. So where is the point? To find the point, guess what you do? Actually, something that we did already before. When the point was not given, you find it by plugging in it to R. You want to go away from t to R. So R of 0, R of 2. You can do it right away, or you can do it later in the progress. And that's how you find the first point at 0 is easy. 1 minus 1, no. R, this. R, yeah, the first point is easy. 1 minus 1 and 0. And the second point, if you plug 2, calculate carefully, is you 5, 3, 0. Thank you for asking. That was a good question. What to plug? What is, so and minus star. That's class. B minus A. Okay, continue. Parametrization. How about, can you do the work done? Question, I don't know, should I put it in it? The work done. I guess kind of is supposed to. How to calculate. I have this here. Work done by the force. And you can, do you remember I was pushing the chair in the classroom if you did not miss the class? So some people in this class never missed any class. Can you imagine? This is so cool. It's like high respect. I should give like extra credit just like for full attendance. Isn't it crazy that some people always should have? That is just so phenomenal. So when I'm pushing the chair, I'm using force to push it. There's a way to find it. Yeah, that's the same chapter basically. Example 9. Example 9, find the work done when I use this force by pushing the chair. How much work I've done to move the particle. And the chair was moving on the floor like in this kind of nice shape of parabola. What an amazing coincidence. But like rails, for example, have lots of parabolas when the train turns and stuff like that. And we even have from where to where. Your main job is to know what formula to use. I feel like that's the hardest part. If you know the formula, everything follows from there. Solution. Work done is used, that's one of the applications of line integral over C. And C in this case is parabola, where C is parabola. Parabola. And we even know from where to where. So in this case, T is not even given. It's right away gives you last point and first point. Solution, let's do parametrization first. I mean, parametrization is not given in this case. So that's why I'm showing this example, parametrization. There's a file I attached in the modules, which lists basic parametrizations. If it is a circle, you know r cosine theta, r sine theta. If it is a cylinder, r cosine theta, r sine theta, z is z. If it is everything else, so sphere has its own, right? Sphere also have whatever, but it's spherical coordinates. But if it's everything else, you usually just, it's usually very stupid if it's not what I just mentioned. Let's choose x to be t, like that's it. Usually it's the same with lines, it's the same with planes, and it's the same with parabolas. It's just convenient to choose your input to be t, and then just find the output. And the output is x squared, so it's t squared. Like boom, done. The only problem, two problems. We need to figure out the orientation and where is t coming from and where does it end. Here's the graph. Let me put it in black. And then blue. Wow, that's ugly. Here's the graph. The blue will be my parabola. Seems like y equals x squared. It's classical parabola. We know that. X, y. So when I need to start from the point 1, 1, that is here, 1, 1. And I need to end at the point 2, 4. That is here, 2, 4. Okay, there is definitely a row from 2. So not down, it goes up. Is it clockwise? Isn't counterclockwise? Doesn't matter. Your job is to make sure it matches. If I put t equals to 0, it's not going to work. Then we start from 0, 0, and we're not starting from 0, 0. Doesn't work. So I'm like, okay, so I need to start from 1. X should be 1, then X matches with T. So that makes sense to use it. Kind of like, yes. Then I'm starting with 1. And X ends up at 2. So 1, 2, 1, 2. Because X matches with T, that is easy to figure out. 1, 2. Now the only thing we need to figure out if direction is correct. Direction is correct from 2. If it's down, if it's going down, if I'm saying from 2, 2 to 1, 1, the picture is the same, everything is the same, but then we're going to reverse. We can put negative here, or we can just reverse the order of T. T is decaying. That makes sense? Yeah. Okay, the moment you have R, where is R? I don't see R. So that's also, some people took effort, which is totally normal, to understand that your R was created. You just created it by yourself. It's T squared. That's your R, because all the formula stems have R, like where is it? That's parameterization. R is a pointing vector. It points at things, and when it points at things, so R, it's actually like this. R points at stuff, and when it points, the curve is being drawn, created. That's how it works.
If the order of the points were different, could you also just like negate the integral, which would like switch the bounds?
I would say we usually change the parameterization. Yeah, not the integral. We change it here. Sometimes we actually make one of those negative. So for example, X, a circle, when it's counterclockwise, that's a positive rotation. X equals R cosine theta, and Y equals R sine theta. If I was told that the rotation is negative, it's not working anymore, and you can check that. Well, R is fixed, say it's like 2. And theta is your T. So that's parameter is T. So if the rotation goes clockwise, then you have to put some negative sign somewhere. So usually it's here. And you can check, then it's going to work. It goes the other way then. You can plug numbers. Usually we just choose some classical numbers like this one. This number is, if radius is 2, I'm gonna zone out for a second. 2 and 0. If you plug 2 and 0, then sine T should be 0, but then cosine T also should be 0. Make correct, but then it matters where does it go, this way or this way. So you change the sign if needed.
But like
I'm not
only
gonna give you negative direction.
Wait, is it like only one of the signs, or like how do you know which one to pick?
Actually, it's creative process. So usually the first one is negative. You can try the second one, and sometimes it's also correct. Remember, parameterization is a creative process. It's not unique. You can have different parameterization with someone else, and the answer will be correct. Parameterization is a pointer, and you can choose which pointer to use. Oh, that's a good way to explain. I can choose to point with a pencil, and then your classmate can choose to point with stick. Doesn't matter. So R can be different. Just make sure it works. That's kind of some of the parameterizations are more obvious than others. That's why they're basic, but actually you can use different ones. For example, to explain, I guess I can just do a different one. If I do X equals T squared, why not? Then Y will be T to the 4. This is also correct. let's do that, you know, so it's creative. That's for parabola, of course. I can do x equals minus 3t for some reason, and y will be 9t squared. But then I have to be careful and check this, like the points should matter. So every time t will have different bounds every time. So for that, we definitely messed up t pretty badly. So I have to figure out bounds carefully, but it also will be correct. So usually people don't make it complicated, so they choose the obvious one. Same with sine and cosine. You could do actually sine and cosine. You can reverse the order. It will be correct as well if you carefully check the signs and everything. But usually people don't do it because there's a standard given. Yeah, parameterization is a tricky thing. Just be open-minded about that. We'll be in the question exam where we're going to have parameterized to find or are, yeah, you will have to do parameterization for sure. We tortured you too much in the homework with parameterization not to give it an exam. And to be honest, it's not like I'm deciding most of it. I received the exam and it definitely asks you a sphere, cylinder, circle, planes, very classical stuff. So nothing too complicated. That's for sure. Well, of course, I'm not saying it's easy, but we only give you stuff you already had before. Nothing new. I just check. I just take stuff from the review and that feels very comfortable. Parameterization. And I don't plan to give you parameterizing planes. There was like one homework with parameterizing planes. I'm still debating if I should give you plane or not. I'm deciding that. But yeah, there was a homework there. I think we were doing it in office hours, so I remember a little bit. What I was trying to say. Oh, let's continue with the question. We found, what are we doing? I already forgot. Oh, we're finding the line integral because it's finishing for work done on the parabola. So first step was parameterization. Second step, figure out your f with that parameterization. F was given x sine y, y. Now it's going to be x is t, y is t squared. So it becomes that. And then you do the dot product of what? Step 3. You can right away find the f dr. Just remember that formula says it's going to be f times r prime dr. So, I mean, you can find it separately, but why not just write it down right away? Integral f is written as vector t sine t squared times, changing the color for you, r prime, stare at your r prime, find derivative of r prime. There's only one variable t, 1 to t, dot product, and you end up with dt. That actually was not correct. R dr is r prime dt. That's the tail, dt. And then you need to figure out where is t running, but we did. T is from 1 to 2, from 1 to 2. That's a dot product. Don't mess up that product. It only multiplies the corresponding components. So it's going to be t sine t squared plus t squared to t, blah, 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 integrate. Figure out something. That is the idea. Also, so that will be a number, and the bigger the number, the more the work were done when I used force to move the chair on the parabola. So that number means stuff, how much force was used and stuff like that. What do you think about that? Okay, good. We are working for 2 hours already. I don't think I can handle more half an hour. So let's speed up a little bit. You will never believe what just happened to the fly. There was a very fat fly flying around and really liking the screen. Green's theorem. Let's briefly remember that. It died. It fell on my table dead. I think the fly did not handle the view examiners. I'm not making this up. It just ended up to be dead on my table right now. I mean, I'm very happy about this because it was super annoying, but like, wow. Okay, even fly died from the review. Green's theorem. On the review, we have it first exam review. know what I'm saying. Theorem, whatever you have. It's definitely on a test. Okay, it's too important not to put it on a test. And it's easier to show the example right away. Example 10, then formulas. If I give you this weird looking integral, don't be afraid. It is a notation. It's just notation. It's nothing really new. This part called P and this part called Q. That's what it is. And then they ask you to find that integral. If C is a segment from -3 to 0 to 3 to 0. Line segment, okay, fine. Line segment. Oh, they have two cases here. That's gonna be taking a while. Fine. And the top half of the circle x squared plus y squared equals to 9. Yeah, that's from your review and from the homework. I remember that. You should remember that too. I remember we were discussing it in the forum, I think. So I don't know the orientation. We actually figured it out, but it's not very hard. If I'm starting from -3 ending to be at 3, right? Then I know it goes positive direction, counterclockwise. To be honest, I don't plan to give you any negative direction, not with line integrals, not with the surface integrals. It's just actually on the final exam, I saw they gave negative direction there. And I decided it's just too mean. People are too stressed. It's going to be 7 p.m. That negative sign will give you wrong answer. Like how just mean is that? I did not feel like doing it. It's nice that you know there's a possibility of it as the knowledge, but taking points off for that. Anyway, it's a closed path. Green's theorem says I can just calculate partial derivative of q with respect to x, subtract partial derivative of y, and integrate that with respect to r. Or like someone mentioned before, you can just find difference and then multiply by the area. So we're shifting. Yeah. Does it make sense? Is it correct? Let me just do that. So finding partial derivatives quickly, let me do at least one piece. Finding partial derivative p with respect to y is 10x. Look at y, look at p and integrate and differentiate with respect to y. Q with respect to x is 20x. Done, put it in the box. The difference then will be 10x if you actually calculate the difference. And then I'm putting inside of the integral. Oh, it should be double integral. I'm like, something doesn't look correct, don't you think so? We're going from single integral into double integral. Fix that. Double. I'm like, that doesn't make sense because we're working as on a line, but then we're switching to D, and D is double integral because D is an area domain. So from C in red, from one integral, we're switching to D, which is in yellow. D is yellow inside. So now we do double integral. Then double integral of 10x will be dx dy, or you can do polar, dr d theta. And you need to figure out what the heck are those, blah, blah, blah. And then you decide what you like here. Polar seems to be easier. So double integral. Polar has a tail. If you do polar, you can choose any. Dx dy will work. It will just have square roots from minus square root and blah, blah, blah. X is happening from minus square root over here to square root over here. half of the circle to half of the circle. And y is happening from 0 to this top piece, which is 3, from 0 to 3. You can do that, but polar seems to be more natural, because then if I have dr to theta, r is from 0 to 3, and theta does not complete the whole cycle. It's half of the circle, so 0 to pi. So it's more natural. But there's a catch. Polar have a formula tail. R pops out. So that's a tail. Don't forget that. So that's kind of the danger of making that mistake. And now we're putting 10x, but you have to change x now. So you need to write down x is r cosine theta. Y is r sine theta. Orientation is positive. Don't have to change anything. R is given. It is 3. That's from here. R is 3. So 3, 3, 3, and x is 3 cosine theta. And you integrate that, and you get the answer. And do you know what answer you get? Can anyone guess the answer? No x term, if we have subtraction, is a constant. There's a question. Oh, yeah, I see what you mean, I think. Do you know the answer of this integral? Did we, so Sydney asks me about this, like, this is a line integral. It's a line integral. Did we complete the cycle? We did. We started from -3 and 0, went to 3 and 0, then we went to the half circle and came back. Do you know the answer? The answer is 0. Duh. And then you can check it is 0. How funny is that? Oh, when do you, oh, there was a question. When do you use times area? Sometimes this is a constant right away. Sometimes it's like some kind of number. Then the thing is that dr d theta or dx dy, this double integral, is some kind of area. So in this case, for example, it's pi r squared over 2 because it's half of the circle. Then you can just multiply by pi r squared over 2. That will speed up the process. And actually, it's already happening. If you integrate this integral right now, you will see pi r squared over 2 in the calculations there. So you can check it out. Yeah, I would check the homework because we have it there. Yeah. If you check the homework, we had several cases when you just, but you can finish integration the way it is. It's just faster if you have a number and you multiply it by the area. Oh, the vector field. Okay, then there was another formula. Check this out. How about this line? How about this integral? Let me think. Okay, let's do new stuff. Recent stuff, 13.7. Let's jump a little bit. Example 11. I would say the most important is, I did very good YouTube video. Did you see? I compared the formulas for you, so that I hope that clarified something. We have small f ds, and we have capital F ds. Those are still, both of them are called surface integrals. Surface integrals, and we have surface area. Remember that we also have surface area, right? So you need to remember all of that. Lots of formulas, unfortunately. So arc lengths, reverse the order, okay, yeah. So surface area is the one with a square root. That's the one actually not too bad. What is the difference? Well, one have capital F and the other one is cannot. No, but in general, like this is a field. So surface area over vector field, that's how it's called. That's the fancy one. That one has formula F times N with a hat. because that normal vector is created by differentiating R first, partial derivatives, from cross product of partial derivatives, not from cross product, just some kind of vectors. So it is F, you plug your R inside as always, but now we're talking about surfaces. So that surface parameterization is happening. U and V times, and that's a dot product, N, and N, let me put it in a different color, and N is RU cross RV, and you don't find the marginal for that. And then it's du dv. Du dv. Remember that. The normal one gives you F. F is a function. So create some kind of surface usually. Double integral over D. And then you have the small f, and the same way you plug your R, but since it's a surface, we need to find parameterization with respect to more variables than just t. Before it was t because it was a curve. Now it's a surface. So parameterization of parabola was not the same thing as parameterization of paraboloid, because one thing is a curve, the other thing is a surface. Surface has orientation outwards and inwards and blah, blah, blah. So that's why it's more complicated. It needs more parameters than just t. It needs 2 parameters. And the more dimensions you go, the more you use, and so on. So just like, maybe one more connection. A circle, we just did a circle. Parameterization of a circle uses just t if we know how far the radius is, right? So we have it here. See, it's only one parameter, in this case theta, but that's actually t. But if we're talking about the sphere, that's a surface already. It's not a curve anymore. And we need 2 parameters. What kind of 2 parameters? If R is fixed, say it is 3, we have 2 parameters, cosine theta sine phi. That's what your U and V are. U and V. If I just said R, it kind of is one more variable. No, it's English. So the higher order of dimension gives you more variables to parameterize, to be used for parameterization. Well, that's a lot of English to talk about. So multiplying by this same idea of RU, RV, cross product, but you take size of that vector, du, dv, magnitude. So that's the big difference. Why? Because surface area. I don't like the SA notation because everywhere in social media they use it for the sexual assault, and now it's kind of bothers me a little bit. So I will use it A. S of A, but in literature I do see as A, and now it's kind of a weird correlation. Surface area. To be honest, surface area doesn't have fixed notation around the world anyways, so you can use anything, even M if you want, who cares? So surface area was also double integral ds, right? Is it correct? Check to make sure. And the thing that we had to figure out R and find RU, RV, and then du, dv. Check if that's correct. Yes, no, 2 people people too tired. Not so many people survived, but some people still here. That's nice. Is this formula correct for surface area? Okay, since nobody's checking, I'll just go check myself. Then go here. Surface integral surface area. Because we're using those parallelograms, that's how I know it is a cross product. Cross product gives you the area of parallelogram, right? And then we need a number. The area is not, I don't want a vector, okay? I need a size. The size means the number, and the number comes from the absolute value, which is magnitude, right? So that's how I remember it personally, but you can use anyway. So, oh, it uses A of S, not S of A. Yeah, that makes sense. I like it more. So, without the function inside, That's a surface area. But the moment you put the function inside, that gives you surface integral with that function, not something unusual, just one more thing to multiply. So let's do it here. Good. Okay, that makes sense.
Wait, I have a question.
Yes.
Yeah, so I understand that like depending on what type of surface you get, like dictates the type of parameters you put in for like U and V. So like, but what happens if you're like given a sphere and you have your X and Y like defined in terms of rho, phi, and theta? Then you're only given like U and V, but you have 3 variables.
Very
So
good
then
question.
what do you pick?
Yeah, very good question. R is fixed. Surface integrals. We have 3 parameters in the spherical coordinates because we're talking about volumes. Triple integrals, if you remember, usually like find the volume, blah, blah, blah. R can be changing. Let me see, where did we go? I already like, oh, here it is. If R is changing, that means I can go from R equals to 0, 1, 2, 3, 4, 5, and that gives me volume. So it kind of gives me a ball, see? So it's a ball, everything filled in. But if it is a sphere and they tell me that it's fixed, we don't need anything below 2 or higher than 2, then it's not a variable anymore. So it's not U and not V, it's 2. So here, if we're talking about a sphere, and that's what we were giving you, a sphere, then U was theta and V was phi. And actually you can keep them in theta and phi. And the rho was a number, any kind of number. So that's where your 2 use, because it's called surface. That's actually took me some time to understand in English, that it makes sense. It's called surface integral. So we only need a shell. For the shell, radius is fixed.
So then does the same principle apply if you're given like cylindrical, then like we're saying Z is fixed?
Exactly. Usually radius is fixed. For the cylinder, if you see also the homework and stuff, it was X, Y, Z. Z usually goes from something to something. So that's usually a variable. But R tells me that I'm not going more than this length. So for example, 2, and then I have cosine U, sine U, which is theta, and Z is V. How do I know? Because Z's keep growing up and down, up and down, up and down. So Z has some kind of variable. So to describe the surface, I need to start from here, for example, and go all over. To rotate, 2 gives me the chance where to rotate. Oh, rotation comes from cosine and sine. They create rotation. But how far do they go? Not more than 2. Actually, no. How far do they go? Only at 2.
So then like your parameters would be like theta and
theta. So let me write down. U is theta. V is Z. Yeah, exactly. Isn't it
thank
weird?
you.
Yeah, super weird. Do you know why? I also have several ways to see it and explain it. It's just maybe confuse people more. That's why I don't defend doing it. But when you have lines, that's when this weird stuff happens. When you just think the same way. Z equals Z. When you have spheres, it's kind of more natural. Any kind of spherical objects like ellipse and stuff. But the moment you have a cone, a line happens. That's this kind of weird. I wanted to say something weird, but that's when the equal sign happens. Same with parabola is fine, but even with lines, parametrize a line like x squared minus plus 2x. You can, usually people choose x equals t and y equals t squared plus 2t. So whatever is not circular, not spherical, usually is weird. That's why cylinder is one of those examples that height is linear. So that's, and it's changing linear. Because if height is not changing, then there's no cylinder. It's going to be just a circle on the floor. Height gives you height of the cylinder. Did that make sense what I just said? Or was like too weird? Oh, more questions. They're all utilized dot product with the integral. Yes, all the dot product. One has, here it is. One has magnitude, the other one doesn't have magnitude. So remember, if you see capital F, field, flux, we're definitely going to give you flux on the test because it's new material. We give you both, actually. Both surface integrals will be on the exam. Flux does not need the size of anything. So you don't do a square root magnitude. But this guy, that's not flux, it's just surface integral. Then this guy needs those parallelograms, and they're coming from the size of the parallelograms. Then, oh, you see it. The question is, where we will be told where you have big F or small f. If you don't see it, they call it flux, then you know it's capital F. But most of the time they do. And I'm actually, let me check on the exam. I do have exam in front of me. I will just make sure that you have it. That it's either small or it's big. Let me see. Curl, find the curl. All of that kind of stuff is here. Find partial derivatives, told you it's here. Don't forget the formula for the arc lengths. Critical points. All of this is in a test. You see, I'm not even afraid to tell you. That's just fact that we had all of that kind of stuff. And spherical, cylindrical, surface area formula. Don't forget that. We just reviewed that. Divergence and curl. Yes, I will give you capital F or not capital F, so that will give you a hint. But if you see flux, you know what to do. That's the hard one. But even flux says capital F, okay? The flux of the vector field F. So in general, the second thing is vector fields. Let's not point at like one specific place. That's called surface integral over the vector field. Vector field. There's electromagnetic fields and stuff like that. In your homework, you also had this example with viscosity. No, it was like velocity times rho. I don't plan to give that. That's like one more formula to remember. Who cares? But yes, there's some applications. Of course, there's so many applications. Surface area. Example of both surface area problems. There's also a question if you have extra credit for practicing exams. No more extra credit anymore. We have everything ready. Small f, big F. There's the one question I missed is formula for A of S. Oh yeah, there was one more formula with a square root, right? There's a question involving sphere parameterization and surface integrals, and that problem took me 3 pages. Very that's something like that. Will be on the exam, and also where there are very long cross products. Spherical parametrizations in surface integrals. No, I mean, of course, all the calculations will be fast. So in general, if you're stuck with long calculations on a test, you're probably doing it wrong. It's like letting you know, the calculations have to be fast. I saw people messing up and then they have like long integrals. I was like, why you guys need so much space? People ask me for extra paper. Oh, because you made a mistake. Then the integral became very complicated. No, when I try to create integrals, they're usually like really good. Very easy to calculate. So, I mean, I gave almost full credit, but it's just like you guys wasted. There was so much time put and effort into calculating so much complicated stuff. What I also wanted to show, oh, so you want to do that, Flex, thank you. Okay, that's example. It was, what is in my notes? Here it is. So I made very good videos on this. Maybe just, you know, watch the video so we don't have to do it now. Let's see. R, U, and V. So create R, or we give you R. You're lucky if we give you R, that's nice. So if I give you sphere, basically I feel confident to give you sphere and cylinder, right? Then you can create R. R is a parameterization. I'm kind of very confident. Everyone in this class should know how to create cylinder parameterization and spherical parameterization. Maybe I should do that. Cylinder parameterization. It's a circle that goes up and down. So x equals r cosine theta, y equals r sine theta, and z equals z. So boom, we have that. But also, do you remember the triple integrals or double integral? What's the tail? That's my question. What is the tail for integration? It was r. No, yes, no. What was the tail? The test reviews tend to have long solutions. R, dz, dr, d theta. Exactly, good job. R. I just remember this way. Polar has r, dr, right? So it's the same as polar, just with dz in it. So r, dr, d theta. But theta always goes at the end. So dz goes first, like so. Remember that. Do you remember directional derivatives? It's like a question for no reason. Do you remember directional derivatives? There was also a question about the other formula. That was surface integral. Surface integral. This is the formula, but then also this is the formula, right? I kind of want to give example. Well, you can actually do both. So just do any you remember. And I mentioned here. No, I personally think it's easier to do the problem the way I did above, which is the first method, instead of rememorizing the next form, the extra form. But it is faster. If the surface is given in a very convenient notation, z equals blah, 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 or y equals blah, 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 then you can, instead of finding cross product, and then so look at this process. Either you do all of that, or you do this. Which one would you choose? It's easy to do the second way if z equals blah, blah, blah is given nicely. Because then you have to find derivatives. Well, you have to find derivatives anyways, but you have to find cross product in size of it. Instead, you can just find 1 plus partial derivative square, partial derivative square. But again, it's the same answer. So technically speaking, I will give you stuff so you can do any way you like, and full credit is yours. So, and I did examples with both. I did example with, here it is, RURV, and you did cross product, and I did example with second formula. Here it is, this one. Z was given very conveniently. Z was a square root of stuff. So I found partial derivatives. And I used, here they are. And I used this formula and it was faster. I have YouTube video solving your last 2 homeworks. So you can check, I used that formula there too to help you out. But you don't have to memorize extra formula. Okay. Do you remember directional derivatives? Should I even put it in the test? I don't know, just like, it's kind of very old material, to be honest. But definitely remember what gradient is. That is must do. I told you, if you leave this class, you must know the gradient. You cannot pass this. You're not supposed to pass this class without gradient. So I'm not supposed to pass you without knowing what gradient is. Gradient and directional derivatives have connection. That's like going to the very beginning. Not very beginning, but directional derivative is duf. You find gradient and then you multiply by u, and u better be unit. U better be unit. So if it's not, you make it unit. And then the answer is a number. I would say if it doesn't say directional derivative vector, then it's not a vector. That's how I would recommend memorizing it. It's a dot product at the end, that's why. And also remember the arc lengths. There was a formula for the arc lengths. Lots of formulas. They do have connection between each other. So it is possible to memorize them, but just kind of annoying. But the formula is size of r prime dt. That's the arc length. Magnitude of the derivative. Because arc length means length of the curve. We are taking those segments and adding them up together. But each segment is r prime. So we don't want to r prime. R prime is the vector. I don't want any direction. I just want to have the size of it. So of course I take magnitude then. Okay, that's too many bars. R prime. So that's how you can memorize. And adding them all together means Riemann sums, and Riemann sums means integration. Oh, that's yeah. And I feel like it's good enough. Oh, that's tangent normal by normal. Yes. Yeah. T and B. We never put B on a test because it's time consuming, but tangent is r prime over size of r prime, right? And is t prime, so you take one more derivative, over size of the t prime. So that's normal. Right or not? Or it's a cross product? No, B is a cross product, and that's when it takes time to figure out. So we don't do B on a test, time consuming. But these two are not too bad. So that's good. Let's see, like, did we cover everything? I have a whole list here, right? So vectors, equations of lines, cross product, dot product, we know that. Equation of lines, equation of planes, space curves, yeah, we did that. Arc lengths and curvature. Velocity acceleration, we did that. What is space curves? Oh, T and B. Yeah, you see? Duh. T and B. Look at this, beautiful. Did you get any of that? I like this. Let me check my notes here. R prime, figuring out tangent vector. Find tangent vector. Yeah. Dot product, cross product. We got it. Okay, done. Multiple variables. I mean, obviously, partial derivatives, chain rule, tangent lines. I don't do linear approximation in any of my classes. We teach them, but I don't like putting them on tests. It's too much to remember. So tangent planes, yes, but approximations, no. Directional derivative and the gradient, we'll discuss that. Means max, discuss that. Double integrals in polar, triple integrals, triple integrals, triple integrals. Yes, you need to know all of these, obviously. And then the last stuff, vector fields. Oh, what is vector fields doing here? So what do we have here? Oh, that's fine. That's a gradient. Conservative, we did that. Gradient field. Yeah, we reviewed that. So I think we reviewed everything. Look at that, so successful. Applications. Illustrate vector by plotting. Yeah, no graphs, thank you, no. A line integral, we did that. Line integral over a vector field. Oh, that's the one. Check it out, check it out. We did that. Line integral over a vector field is when you collect all those numbers, right? And if it's positive and big, that means the force was helping me. For example, the wind was blowing into my back. When I was walking fast. If it's negative but big, that means it was really into my face and I was slowing, and it was so strong because the number is big but negative. If it's 0, I did not feel the wind towards my face or towards the back. So it's collecting those arrows on the way. Look at that. See, how cool is that? So when I go this way, it helps me. Back doesn't help me, against me, perpendicular, and so on. So we already covered that right now. See, ta-da! Line integrals, f times r prime. We covered that. I think I covered everything. Yeah, here's what I just said. Big negative or big positive. Oh, and the work done. So we just covered that. Actually, this is the example I just covered. The parabola one. Green's theorem, we covered. Pearl divergence, covered. Parametrization, covered. Surface area, covered. Surface integrals, 2 cases, covered. This is the problem I did, your homework problem. Number 8 and number 9. This is my YouTube video from yesterday. Flux. Flux is on the test. Make sure you know flux. That's the crew input. And again, it can be upwards or inwards. I will give you positive orientation for everything. Mobius strip. Tra-la-la, formulas. You need to know formulas, basically. And I will not give you unusual parameterization to make, like helicoid. I'm not going to expect you to remember helicoid. So if there's helicoid, I'll give you. But again, cylinder and sphere and circle, you know these parameterizations, so I feel comfortable giving it. Good, check it out. I think we did very good. That took me like 2.5 hours, a bit more than that. I'll give you the video and the notes. The notes are already posted, actually, in the modules. I will attach to the announcement, so you don't have to look for it. So it's a lot to remember. I do understand, especially if you have other exams like physics, chemistry, engineering, lots of formulas to remember. So good luck, study hard, and I definitely rooting for you to do well on the test. I'll see you on Tuesday, most of you, at 7 p.m. Well, it's 7:10, but I always say 7 p.m. Don't be late, come early. We're gonna listen to some music. Maybe I'll bring some MMMs. We can eat MMMs. And that's it. My suggestion is always, when the exam starts, you have your paper, write down the formulas. Like, you know, I don't know, maybe not all of them, but like the more the better. Whatever you're afraid to forget, you grab your paper. When I give you exam, you have rights to write down everything, including whatever bothers you to forget. Write down some crappy formulas which are hard to remember, which I think line integrals over the vector field, not vector, write them down. So review them like 5 minutes before the exam. Put your notes away. I give you paper, write them down and release it from your memory. Right? That's how I did it. And you see, I succeeded. So good job, people. Thank you for staying so late. So many people stayed. Good job. I'm going to post everything. Hopefully this is enough for your success because I tried everything, I think. Now it's up to you. And I'll see you on Tuesday. Good luck with other exams as well. Wish you the best. Bye-bye.
Thank you.
Thank you for coming. Good job for staying for so late. What is that? Probably.